Imagine stepping outside late at night when the world has finally quieted down. The streets are empty, the air is still, and above you stretches a sky filled with distant points of light. For thousands of years, humans have looked up at that sky and asked a simple question that slowly becomes deeper the longer you sit with it. What exactly is all of this? For most of human history, the answer seemed straightforward. The universe was everything that existed. Every star, every planet, every cloud of gas, every distant glow of light in the night sky. It was the whole story, the complete stage on which reality unfolds. But as science advanced, something unexpected happened. The more carefully we studied the cosmos, the larger and stranger it became. The Earth was no longer the centre. Our sun turned out to be one ordinary star among hundreds of billions inside the Milky Way. And the Milky Way itself was only one galaxy among trillions scattered across the vast observable cosmos. With each new discovery, the universe seemed to grow not only larger, but also more mysterious. And eventually, a new and unsettling idea began to appear in the minds of physicists and cosmologists. What if the universe we see is not the whole story? What if our cosmic home is only one region within a far larger reality? A reality where multiple universes might exist side by side, each with its own history, its own physical conditions, and perhaps even its own laws of nature. This possibility is often called the multiverse. At first hearing, the word can sound almost like science fiction, a collection of parallel worlds, endless copies of reality, different cosmic domains where the rules themselves may change, and because of that, the multiverse idea has sparked intense debate. Some scientists believe it may be one of the most profound predictions of modern physics, emerging naturally from theories about cosmic inflation, quantum mechanics, and the deep structure of space itself. Others argue that the multiverse may stretch science too far, turning explanation into speculation. If other universes exist but can never be observed, they ask, can the idea truly belong to science? Tonight we will explore this question slowly and carefully. We will not rush to conclusions. Instead, we will walk step by step through the ideas that led physicists to even consider such a possibility in the first place. We will explore how our understanding of the word universe has quietly evolved over time. We will look at the limits of what we can observe and how the horizon of our cosmic vision may hide vast unseen regions. We will encounter theories suggesting that the laws of physics might not be identical everywhere. We will examine the curious problem of cosmic fine-tuning and the strange possibility that life can exist only in very special types of universes. And along the way, we will gently step into the philosophical questions that arise when science reaches the edge of what can be tested. Questions about simplicity, questions about explanation, and questions about whether reality might be far larger and far richer than a single universe alone. The journey will take us through cosmology, quantum physics, and the quiet philosophical corners of science where certainty becomes rare and curiosity becomes essential. But throughout this exploration, we will keep one important idea in mind. The multiverse is not simply a wild speculation invented out of thin air. Instead, it appears as a possible consequence of several serious scientific theories. The same theories that attempt to explain the birth of our universe, the behaviour of particles, and the structure of space and time itself. Whether those consequences turn out to be real is still an open question, and perhaps that uncertainty is part of what makes the idea so fascinating. Because sometimes the most interesting discoveries in science begin not with answers, but with the quiet realization that the universe may be far stranger than we first imagined, and that realization leads us to the first step of our journey. Before we can ask whether there might be many universes, we need to slow down and ask a simpler question. What do we actually mean when we say the word universe? If you were able to travel far away from the lights of cities, far from highways and buildings and glowing windows, you might eventually find yourself under a sky so dark and clear that the stars appear almost overwhelming. In places like the high deserts of Chile, the mountains of Hawaii, or the quiet plains of central Australia, the night sky can look less like scattered dots of light and more like a soft river of distant suns stretching from horizon to horizon. Under such a sky, something curious tends to happen to the mind. The ordinary scale of daily life begins to shrink. The concerns of the day become quieter, and in their place, a deeper question slowly begins to emerge. Where does all of this end? For much of human history, the universe seemed relatively simple to imagine. Ancient astronomers saw the stars as fixed lights embedded in a celestial sphere. The cosmos was vast, certainly, but it was still imagined as a single, orderly structure surrounding the Earth. That picture began to change dramatically during the scientific revolution. When Nicholas Copernicus proposed that the Earth moves around the Sun, it was more than just a new model of the solar system. It was the first step in removing humanity from the centre of the cosmic story. Later, Galileo's telescope revealed mountains on the Moon, moons orbiting Jupiter, and a sky filled with far more stars than the naked eye could see. Each discovery quietly pushed the boundaries of the universe outward. Centuries later, astronomers realized that the faint spiral shapes seen through telescopes were not clouds inside our galaxy at all. They were entire galaxies themselves, vast islands of stars scattered across enormous distances. Our Milky Way, once thought to contain everything, suddenly became only one member of a much larger cosmic population. Today, modern telescopes such as the James Webb Space Telescope allow astronomers to peer deep into space and deep into time. Some of the galaxies we observe emitted their light more than 13 billion years ago, not long after the universe itself first began expanding. From these observations, scientists have constructed a remarkable picture of cosmic history. About 13.8 billion years ago, the universe was in an extremely hot, dense state. Space itself began expanding, cooling as it grew. Matter formed into atoms. Atoms gathered into stars. Stars assembled into galaxies. And over billions of years, gravity slowly sculpted the vast cosmic web we see today. This expanding cosmos contains an extraordinary number of stars. Astronomers estimate that there may be roughly 2 trillion galaxies within the observable universe, each containing anywhere from millions to hundreds of billions of stars. Even these numbers are difficult to truly imagine. If every star in the Milky Way were represented by a single grain of sand, the entire galaxy would form a beach several kilometers long. And yet, the Milky Way itself would be just one grain among countless others scattered across the cosmic shoreline. For many people, this immense scale already feels almost beyond comprehension. But something even more intriguing appears when physicists look closely at the limits of what we can actually observe. Because the observable universe is not the same thing as the entire universe. There is a boundary to how far we can see, not because space ends there, but because light itself travels at a finite speed. Light from extremely distant regions may simply not have had enough time to reach us since the beginning of cosmic expansion. This means that the universe we can observe is like a glowing sphere centered on our position in space, defined by the distance light has been able to travel during the lifetime of the cosmos. Beyond that sphere may lie more galaxies, more stars, and more regions of space forever hidden from direct observation. Already then, we find ourselves in a curious situation. The universe we see may be only a portion of a much larger whole. And once that possibility enters the conversation, a new idea slowly begins to take shape. If there are regions of space forever beyond our observational horizon, could those regions be very different from our own? Could the cosmos contain vast domains separated not by walls, but simply by distance so enormous that light from those regions will never reach us? And if such regions exist, might they represent something that begins to resemble the earliest and simplest version of a multiverse? This is where the story of the multiverse truly begins, not with wild speculation, but with a quiet realization. The universe we observe may not be the entire stage of reality. It may simply be the part of the stage illuminated by the light that has had time to reach us. For most of human history, the word universe carried a meaning that felt absolute. It referred to everything that exists, every star, every planet, every cloud of gas, every grain of dust drifting through space, and every corner of reality itself. The universe was understood as the totality of existence, the complete collection of all things that are real. Under that definition, the idea of a multiverse would seem almost impossible. If the universe already includes everything, then there is simply no room left for another one. Yet as science has progressed, something subtle has happened to this word. The meaning of universe has quietly shifted. This shift did not happen because scientists wanted to create new mysteries. Instead, it emerged naturally as our understanding of cosmology grew more precise. To see how this happened, it helps to imagine the universe not as a philosophical concept, but as a physical object with a history. Modern cosmology tells us that the cosmos we inhabit began about 13.8 billion years ago in an extremely hot and dense state. Space itself was compressed into a tiny region, filled with energy so intense that ordinary matter could not yet exist. As the universe expanded and cooled, the first simple particles formed. Later, those particles combined into atoms. Over hundreds of millions of years, gravity slowly gathered those atoms into stars and the stars into galaxies. The universe we observe today is the result of that long cosmic evolution. When cosmologists speak about the universe in this context, they often mean something more specific than the philosophical idea of everything that exists. They mean a continuous region of space and time that emerged from a particular cosmic beginning and has evolved according to a particular set of physical conditions. In other words, a universe in modern physics can be thought of as a single cosmic history. It is one connected space-time region with its own origin, its own expansion, and its own physical environment. Once this shift in meaning occurs, the possibility of multiple universes begins to make more sense. If a universe is defined as one continuous space-time region with its own cosmic history, then the existence of multiple such regions is not automatically contradictory. Instead, it becomes a scientific question. Could there be other space-time regions separate from ours that experience their own beginnings and their own evolutions? Could reality contain multiple cosmic domains, each following the same fundamental physical principles but unfolding in different ways? Or perhaps even domains where the conditions of physics differ slightly, producing universes that look very different from our own? At this stage, the idea still remains cautious and restrained. We are not yet imagining wildly different worlds with entirely alien rules. Instead, we are simply recognizing that our traditional definition of the universe may have been too narrow. It is similar to how the concept of a continent evolved as humans explored the Earth. At one time, a small portion of land might have been thought of as the entire world. Only later did explorers realize that the land they knew was just one region within a much larger planet. Likewise, the cosmic region we observe may be only one part of a broader reality. And this leads to another important insight. Even within our own observable cosmos, the laws of physics appear remarkably consistent. The same basic rules governing gravity, electromagnetism, and particle interactions seem to apply across billions of light years. But this observation raises an interesting question. Are those laws truly identical everywhere? Or have we simply not looked far enough to find regions where they might differ? If reality extends far beyond the limits of our observation, it becomes possible that other cosmic regions could exist where the conditions are slightly different. Different values for certain physical quantities, different arrangements of fields that shape the behavior of matter. Perhaps even entirely separate cosmic expansions unfolding far beyond the horizon of our own. At first, this idea might sound speculative, but it turns out that several important areas of modern physics naturally open the door to this possibility. Theories developed to explain the early moments of the universe, the behavior of quantum systems, and the structure of fundamental forces sometimes produce models in which many universes emerge naturally. In these models, the multiverse is not an extra invention added for dramatic effect. Instead, it appears as a consequence of the underlying physics. That is why the multiverse concept has attracted so much attention. It sits at the intersection of cosmology, particle physics, and the philosophy of science. It challenges our assumptions about the scale of reality and forces us to reconsider what we really mean when we say that something exists. But before exploring those deeper theories, it is helpful to pause and reflect on one more subtle point. When we speak about the universe today, we're often referring not to everything that exists, but to the particular cosmic region whose light has had time to reach us. In other words, our universe may be defined not only by its physical history, but also by the limits of our observation. And those limits are determined by one of the most important features of physics itself, the speed at which light travels. Because light moves at a finite speed, there are regions of space so distant that their light has simply not yet arrived here. Those regions may still exist. They may contain galaxies, stars, and entire cosmic structures. But for now, they remain hidden beyond the horizon of our observable universe. Understanding this horizon is the next key step in the story, because once we recognize that our view of the cosmos is limited by the travel time of light, we begin to see how the universe we observe might be only a small portion of a much larger reality. And that realization leads us gently toward the next stage of our journey, the idea that even within our own universe, vast regions may lie forever beyond our view. Long before the idea of multiple universes entered scientific discussions, cosmologists encountered a simpler but equally profound realization. Our view of the universe is limited, not because space necessarily ends at some distant boundary, but because light itself requires time to travel. This fact may sound ordinary at first. We're used to thinking of light as incredibly fast, and indeed it is. Light moves through empty space at about 300,000 kilometers every second. At that speed, it can circle the Earth several times in a single second, and yet even this astonishing speed is not infinite. Because light takes time to travel, looking out into space is also a way of looking backward in time. When we observe the moon, we see it as it was a little more than 1 second ago. The light leaving its surface takes just over a second to reach Earth. When we observe the sun, we see it as it was about 8 minutes in the past. That is how long sunlight needs to cross the distance between our star and our planet. The farther we look into space, the farther we look into history. Light from the nearest stars requires several years to arrive. Light from distant galaxies may take millions or even billions of years before reaching our telescopes. In this way, astronomy becomes a kind of natural time machine. Each observation captures a moment from the deep past of the cosmos. But this remarkable feature of light also introduces an important limit. If the universe has existed for about 13.8 billion years, then light from extremely distant regions may simply not have had enough time to reach us yet. Even if galaxies exist far beyond our current view, their light could still be travelling toward us, slowly crossing the vast distances of expanding space. This leads scientists to define a concept known as the observable universe. The observable universe includes everything whose light has had time to reach us since the beginning of cosmic expansion. It is the region of space we can, in principle, observe from our position. Imagine standing in the middle of a dark field with a lantern. The light from the lantern spreads outward in all directions, forming a glowing circle around you. Inside that circle, objects are visible. Outside the circle, there may still be trees, hills, or distant buildings, but they remain hidden in darkness because the light has not yet reached them. In a similar way, our observations of the cosmos form a kind of sphere of visibility centered on Earth. This sphere is enormous. Today, astronomers estimate that the observable universe stretches roughly 46 billion light-years in every direction. This number may seem surprising at first because the universe itself is only about 13.8 billion years old. But space has been expanding during that entire time, carrying distant galaxies farther away even as their light travels toward us. The result is that the most distant galaxies we can observe today are much farther away than the distance their light has travelled. Inside this vast sphere lie trillions of galaxies, each containing vast numbers of stars, planets, and clouds of gas. Everything we've ever observed in cosmology exists within this immense cosmic bubble. Yet the observable universe is not necessarily the entire universe. It is simply the portion that light has had time to reveal. Beyond that horizon may lie additional regions of space, filled with galaxies and cosmic structures similar to our own. Those regions may follow the same physical laws we observe here. They may contain familiar types of stars and galaxies. In many models of cosmology, there is no reason to believe the universe suddenly stops just beyond the edge of what we can see. Instead, space may continue outward indefinitely. The boundary separating the observable universe from the unseen cosmos is often called the particle horizon. Despite its dramatic name, the particle horizon is not a wall or barrier. It is simply the farthest distance from which particles or light could have travelled to reach us since the beginning of the universe. It marks the edge of what is observable from our current location. Beyond that distance, light has not yet had enough time to arrive. This idea leads to an important and sometimes surprising conclusion. Two observers located in very distant regions of the universe may each possess their own observable sphere of space. Each observer would see galaxies around them extending outward in every direction. But their observable regions might not completely overlap. There could be galaxies visible to one observer that are permanently invisible to the other. In this way, the universe contains multiple observational horizons, depending on where an observer happens to be located. Already then, we encounter a curious feature of cosmology. The universe may be far larger than the region we can ever directly observe, and if space truly continues far beyond our horizon, then the unseen cosmos could contain an enormous number of galaxies and cosmic structures stretching into distances so vast that their light may never reach us. This realization represents the earliest and simplest step toward the idea of a multiverse. At this stage, we are not yet imagining separate universes with different laws of physics. Instead, we are simply recognizing that our observable region may be only one small part of a much larger cosmic landscape. If space extends far enough, then distant regions of the universe could evolve in ways very different from our own. Galaxies might form, earlier or later. Matter might cluster into different patterns. Entire cosmic histories could unfold beyond our observational horizon without us ever knowing. Some physicists refer to this possibility as a quilt multiverse. The idea is simple. If space is extremely large, perhaps even infinite, then the cosmos may resemble an enormous patchwork quilt. Each patch represents a different region of space with its own arrangement of galaxies and matter. The underlying laws of physics remain the same, but the details of cosmic history vary from place to place. In such a universe, distant regions might contain structures that look very different from our own corner of space. Some areas might be more densely packed with galaxies. Others might be emptier cosmic voids. And in an infinite cosmos, the patterns of matter could eventually repeat themselves in distant regions far beyond our reach. The idea may sound strange, but it arises naturally from a simple realization. The observable universe is limited not by the edge of reality, but by the travel time of light. And once we accept that our view of the cosmos is incomplete, the possibility emerges that reality may extend far beyond the luminous sphere we can see. That quiet realization forms the first gentle step toward the multiverse, not as a sudden leap into exotic speculation, but as a natural consequence of the limits placed on observation by the speed of light itself. Once we understand that the observable universe is limited by the travel time of a light, a quiet but important possibility begins to appear. The region we can see may be enormous, but it may still represent only a small part of a much larger reality. To explore this idea, imagine standing on the shore of a vast ocean during the night. The light from a distant lighthouse illuminates only a small circle of water around you. Within that circle, you can see waves, reflections, and the movement of the tide. But beyond the glow of that light, the ocean continues into darkness. There may be distant ships, islands, or entire coastlines hidden beyond what your eyes can reach. In a similar way, the observable universe is the region illuminated by the light that has had time to reach us since the beginning of cosmic expansion. But nothing in our current understanding of cosmology requires space itself to end just beyond that boundary. In fact, many cosmological models suggest that space may extend far beyond what we can observe. Some models even allow the possibility that the universe is spatially infinite, meaning that it stretches outward forever without an edge. If that were true, the consequences would be both fascinating and slightly unsettling. Because the universe is made from a finite set of building blocks. The particles that form atoms, the atoms that form stars, and the forces that shape galaxies follow consistent physical laws. These building blocks can combine in many different ways, but the number of possible combinations within any limited region of space is not unlimited. If space continues far enough, those combinations may eventually repeat. This idea may sound strange at first, but it is actually a simple consequence of probability. Imagine shuffling a deck of playing cards. Each shuffle produces a new arrangement of the same 52 cards. There are an enormous number of possible arrangements, far more than a person could ever produce in a lifetime of shuffling. But if someone continued shuffling forever, eventually some arrangements would repeat. Not because the deck is small, but because the number of possible arrangements, though extremely large, is still finite. In a similar way, the matter within a large region of space can form an immense variety of cosmic structures. Stars can gather into galaxies. Galaxies can form clusters and vast filaments stretching across space. Planets may orbit around distant suns, and complex chemistry may arise in certain environments, but if the universe is large enough, these patterns of matter may eventually occur again in distant regions. This concept leads to what physicists sometimes call the quilt multiverse. The name comes from the image of a patchwork quilt spread across an enormous surface. Each patch contains a different pattern stitched from the same threads. In this analogy, the threads are the fundamental particles and forces of nature. The patches are different regions of the universe, each containing its own arrangement of galaxies, stars, and cosmic structures. From a distance, the entire quilt forms one continuous object, but locally, each patch can look quite different. In some regions of the cosmic quilt, galaxies might be densely clustered together. In others, vast empty voids might stretch across millions of light years. Certain regions may contain stars that formed earlier in cosmic history, while others may have taken longer to assemble. And in an extremely large universe, there could even be regions where the arrangement of matter closely resembles our own cosmic neighbourhood. Some physicists have estimated that if space extends far enough, there could exist regions where the pattern of galaxies is almost identical to the one we observe around us. In even more distant regions, it is theoretically possible that the arrangement of atoms might match those found on Earth. This would not mean that another Earth was deliberately created, or that reality is copying itself intentionally. Instead, it would simply reflect the enormous scale of the cosmos and the statistical repetition of patterns when the number of regions becomes unimaginably large. Yet even this idea does not require a universe that is literally infinite. An extremely large universe could produce similar effects. If space extends far beyond our observable horizon, then the number of cosmic regions may still be vast enough that many different arrangements of matter occur somewhere. In this picture, the multiverse does not consist of completely separate universes floating in isolation. Instead, it is one enormous cosmic structure containing many distant regions, each with its own local history. These regions follow the same physical laws we observe here. Gravity behaves the same way. Atoms form in the same manner. Stars ignite through the same nuclear processes. The difference lies not in the laws themselves, but in the specific arrangements of matter and energy. This version of the multiverse is therefore the most conservative. It does not require new physics. It does not require different laws of nature. It simply follows from the possibility that space may be far larger than the portion we can observe. Many cosmologists refer to this as a natural extension of the cosmological principle. The cosmological principle is the idea that, on large scales, the universe looks roughly the same in every direction and from every location. In other words, our position in the universe is not special. If this principle holds across extremely large distances, then distant observers in other galaxies would see a cosmos that appears broadly similar to ours. Their observable universe would also be filled with galaxies and cosmic structures extending outward in every direction. Yet their horizon of observation would be centered on their location, not ours. Each observer would therefore inhabit a different region of the same enormous cosmic quilt. This simple picture already stretches our imagination. The universe we see might be only one patch in a cosmic fabric that extends far beyond our observational horizon. And while the laws of physics remain the same across this vast structure, the details of cosmic history could vary from place to place. But as cosmologists continued exploring the early moments of the universe, another idea emerged that pushed the multiverse concept even further. According to some theories of cosmic expansion, the universe may not simply contain many distant regions. It may actually generate entirely separate cosmic domains, each with its own beginning. And that idea begins with a remarkable event thought to have occurred in the earliest fraction of a second after the universe was born, a moment when space itself expanded at a staggering rate, a moment known as cosmic inflation. In the previous part of our journey, the multiverse appeared as a quiet consequence of cosmic scale. If space is extremely large, perhaps even endless, then distant regions may contain different arrangements of matter. The laws of physics remain the same everywhere, but the details of cosmic history vary from place to place. Yet during the late 20th century, cosmologists began exploring another possibility. What if the early universe itself created many separate cosmic regions? This idea begins with a remarkable event believed to have occurred during the first moments of cosmic history. Today, astronomers observe that the universe is expanding. Galaxies are moving away from one another as space itself slowly stretches. This expansion was first noticed in the early 20th century, when astronomers studied the light from distant galaxies and discovered that their wavelengths were slightly shifted toward the red end of the spectrum. That shift revealed that those galaxies were receding from us. If the universe is expanding today, then it must have been smaller and denser in the past. Tracing this expansion backward leads to the idea that the universe once existed in a very hot and compact state. But when physicists studied the details of that early state, they encountered several puzzling questions. One of these puzzles involved the remarkable uniformity of the cosmos. When astronomers measure the faint glow left over from the early universe, a signal known as the cosmic microwave background, they find that the temperature of this radiation is almost perfectly uniform across the entire sky. Regions separated by enormous distances appear to share nearly identical temperatures. Yet according to simple models of cosmic expansion, those regions should never have had enough time to exchange energy or information with one another. In other words, they should not have been able to coordinate their temperatures so precisely. To solve this puzzle, physicists proposed a dramatic idea. In the earliest fraction of a second after the universe began expanding, space itself may have undergone a brief period of extremely rapid expansion. This event is known as cosmic inflation. During inflation, space did not merely expand at the gentle pace we observe today. Instead, the scale of the universe may have increased at an extraordinary rate. Tiny regions of space were stretched outward until they became large enough to encompass the entire observable universe we see today. This sudden growth could explain why distant parts of the cosmos appear so similar. Before inflation occurred, those regions may have been much closer together, allowing them to reach a common temperature. When inflation stretched space outward, it carried those once neighbouring regions far apart. Inflation also provides an elegant explanation for why the geometry of the universe appears remarkably smooth on large scales. Just as the surface of a balloon appears flatter when it's inflated, the rapid stretching of space could smooth out irregularities in the early cosmos. But as physicists explored inflation more deeply, an even more surprising possibility emerged. In some versions of the theory, inflation does not stop everywhere at the same time. Instead, it ends in certain regions while continuing in others. To visualize this idea, imagine a pot of water gently heating on a stove. As the water approaches boiling, small bubbles begin to appear in different places. Each bubble forms when the water in that local region changes state. While one bubble forms and rises, the surrounding water may still be heating and forming new bubbles elsewhere. In certain models of inflation, the universe behaves in a somewhat similar way. The background of space continues expanding rapidly in an inflationary state, while small pockets of space occasionally transition out of that state. Each pocket becomes a region where inflation ends and a more familiar cosmic evolution begins. Inside these pockets, space expands more slowly. Matter forms, galaxies eventually appear, stars ignite and begin shining. Each of these pockets can be thought of as a universe. Our own universe may be one such bubble that formed within a much larger inflating cosmos. Outside our bubble, inflation may still be continuing, stretching space at an extraordinary rate and generating new bubbles elsewhere. This idea is known as eternal inflation. The word eternal does not necessarily mean that inflation lasts forever in time, although some models allow that possibility. Instead, it reflects the idea that the inflationary process can continue, producing new regions even as older regions settle into calmer cosmic histories. In this picture, the larger inflating space resembles an enormous cosmic ocean. Within that ocean, countless bubble universes form and drift apart as space expands. Each bubble contains its own expanding region of space-time, its own galaxies, and its own cosmic history. most of these bubbles would be unimaginably distant from one another, separated by vast stretches of inflating space expanding faster than light could ever travel between them. This means that once a bubble universe forms, it quickly becomes isolated from its neighbours. Signals from one bubble would never reach another. From the perspective of observers inside a bubble, their universe would appear to be the entire cosmos. They would see galaxies expanding away from one another and measure a cosmic history beginning with a hot, dense early state. In many ways, their observations might look remarkably similar to our own. Yet their universe would represent only one small region within a far larger multiverse. Physicists such as Alan Guth and Andre Linde helped develop this idea during the 1980s and 1990s, exploring how inflation could naturally lead to a cosmic landscape filled with bubble universes. For some researchers, eternal inflation provides one of the most compelling theoretical routes toward a multiverse. It arises not from speculative imagination, but from attempts to understand the earliest moments of cosmic history. At the same time, eternal inflation raises profound questions. If countless bubble universes exist beyond our reach, each separated by rapidly expanding space, how could we ever confirm their existence? Could traces of other bubbles leave subtle marks in our own cosmic history? Or might these neighbouring universes remain forever beyond our observational horizon? These questions continue to challenge cosmologists today. But before turning to the question of evidence, there is another fascinating possibility to explore. Some theories suggest that universes may not only emerge from inflation, they may also be born in one of the most extreme environments known in the cosmos, inside black holes themselves. By this point in our journey, the idea of multiple universes has already appeared in two different ways. First, through the immense scale of space itself. If the universe extends far beyond our observable horizon, then distant regions may contain different arrangements of matter, forming a kind of cosmic patchwork across unimaginable distances. Second, through the theory of cosmic inflation. In certain models of inflation, space may produce countless expanding bubble universes, each emerging from a background of rapidly expanding space. But there is yet another place in the cosmos where physicists have wondered whether new universes might be born. Strangely enough, that place may lie inside black holes. Black holes are among the most extreme objects known in nature. They form when a large amount of matter collapses under the pull of gravity, compressing into a region so dense that not even light can escape its grasp. When a massive star exhausts the nuclear fuel in its core, gravity can cause the star to collapse inward. If enough mass is concentrated in a small enough region, the escape speed required to leave that region becomes greater than the speed of light. At that point, a boundary known as the event horizon forms. The event horizon marks the point of no return. Once matter or light crosses this boundary, it cannot escape back into the surrounding universe. For observers outside the black hole, the interior becomes hidden behind this horizon. Inside that hidden region, gravity continues pulling matter inward. According to Einstein's theory of general relativity, this collapse leads toward an extremely dense state often called a singularity. In that state, the known laws of physics break down and our mathematical descriptions of space and time can no longer fully describe what is happening. But some physicists have suggested that the story might not end there. Instead of collapsing into a final singular point, the interior of a black hole might transition into a new expanding region of space-time. In other words, the gravitational collapse that forms a black hole in one universe could potentially give rise to a new universe on the other side. From the perspective of observers inside that new region, the event that created their universe might look very much like a Big Bang. Space would begin expanding, Matter and radiation would fill the young cosmos. Over time, galaxies and stars might eventually form. Meanwhile, to observers outside the black hole, the new universe would remain completely hidden beyond the event horizon. This idea has been explored in various theoretical models, sometimes referred to as black hole cosmology. One physicist who developed an intriguing version of this idea is Lee Smolin. In the 1990s, Smolin proposed a concept known as cosmological natural selection. The basic idea draws inspiration from biological evolution. In biology, organisms reproduce, and those that reproduce more effectively tend to pass their traits to future generations. Over time, natural selection can shape the characteristics of species. Smolin wondered whether something loosely similar might occur at the cosmic scale. If black holes can create new universes, then universes that produce many black holes might generate more offspring universes than those that produce few. Over many generations, the physical conditions of universes might gradually shift toward values that encourage the formation of black holes. Interestingly, many of the same conditions that allow stars and galaxies to form also allow black holes to form. This means that a universe capable of producing complex cosmic structures might also be particularly good at producing new universes. Although this idea remains speculative, it illustrates an important point. Multiple universes need not arise from a single theory alone. Different branches of theoretical physics sometimes point towards similar possibilities through entirely different paths. Another path toward multiple universes appears in models where the cosmos undergoes repeated cycles of expansion and contraction. In these cyclic universe models, the universe does not experience only a single beginning. Instead, cosmic history may consist of many phases. In one phase, the universe expands and cools. Galaxies form, stars burn, and cosmic structures develop over billions of years. Eventually, the expansion may slow or change, leading the universe toward a new stage. In some models, the cosmos might eventually contract again, shrinking toward a dense state that triggers a new expansion phase. Each cycle would resemble a rebirth of the cosmos. Instead of a single Big Bang, there would be a sequence of cosmic eras, each emerging from the remnants of the previous one. Some theories describe this process as a bounce rather than a collapse. Rather than ending in a final singular state, the universe might compress and then rebound into a new expansion phase. Over immense stretches of time, countless cosmic cycles might unfold. Each cycle could produce slightly different conditions for the formation of matter, galaxies, and stars. Although cyclic cosmology does not always produce separate universes in the same sense as eternal inflation, it still challenges the idea that our cosmic history is unique. Instead, the universe may have experienced many beginnings. Each beginning would represent a new chapter in the larger story of cosmic evolution. What makes these ideas particularly fascinating is that they emerge from attempts to understand gravity, quantum physics, and the earliest moments of the cosmos. They are not simply imaginative stories about parallel worlds, they are proposals arising from the effort to extend our theories into the most extreme environments known in nature. Of course, many of these ideas remain highly uncertain. Black hole cosmology, cosmic natural selection, and cyclic universe models all face difficult theoretical challenges. Physicists are still working to understand how gravity behaves under the most extreme conditions, and how quantum effects might alter our picture of the early universe. Yet even with these uncertainties, one pattern has become clear. The deeper we investigate the origins of the cosmos, the more often the possibility of multiple universes appears. Different theories, developed for different reasons, sometimes point toward a similar conclusion. Reality may be capable of producing many cosmic domains. Some may be separated by immense distances across space. Others may arise from the birth of new space-time regions within black holes. Still others may emerge through repeating cycles of cosmic expansion and rebirth. And as these ideas continued to develop, physicists began to confront an even deeper question. If multiple universes exist, might the laws of physics themselves vary from one universe to another? For most of human history, the laws of physics were imagined as something absolute. Gravity pulls objects toward one another, light travels through space, matter forms atoms, atoms form molecules, and molecules build the structures we see around us. These rules appear so reliable that we often assume they must be identical everywhere in the universe and at all times. And in many ways, that assumption has worked remarkably well. Astronomers observe galaxies billions of light years away, and the same basic physical processes seem to apply. Stars burn through nuclear fusion in distant galaxies just as they do in our own. Gravity shapes cosmic structures in the same way across enormous distances. But as physicists began examining the deepest layers of reality, a more subtle picture began to emerge. The laws we observe may not be simple rules written directly into the fabric of the universe. Instead, they may arise from deeper physical structures known as fields. In modern physics, a field is something that exists throughout space. Rather than thinking of particles as tiny isolated objects, physicists describe them as small ripples or excitations within these underlying fields. For example, the particles of light are understood as disturbances in an electromagnetic field that fills all of space. Similarly, other particles arise from their own corresponding fields. These fields are not confined to specific locations. They extend everywhere, even through regions that appear empty. Space, in this sense, is not truly empty. It is filled with a quiet background of physical fields that define how matter and energy behave. What makes this idea particularly interesting is that these fields can exist in different energy states. To understand this, imagine a landscape of hills and valleys. If you place a ball somewhere on that landscape, gravity will cause it to roll downward until it settles into a valley. That resting position represents a stable state. But the landscape might contain many valleys, not just one. A ball placed in one valley might remain there indefinitely, while a ball placed in another valley might settle into a different resting position. Each valley represents a possible stable configuration. In physics, something similar may occur with certain fields that fill the universe. The lowest energy state of a field is often called its vacuum state. Despite the name, this does not mean empty space in the ordinary sense. Instead, the vacuum state describes the quiet background condition of a field when it is not actively producing particles. But just like the valleys in our imagined landscape, a field may have more than one possible resting state. Different regions of space could, in principle, settle into different configurations. If that happens, the physical properties of those regions could be different. The masses of particles might change slightly. The strengths of certain forces could vary. Even the types of particles that can exist might depend on the local configuration of these fields. In such a situation, the underlying laws of physics would remain the same at the deepest level. But the way those laws are expressed in a particular region of the universe could differ. It is similar to how the same musical instrument can produce many different notes. The instrument itself follows the same physical principles everywhere, but the specific sound that emerges depends on how the instrument is played. In the same way, the fundamental structure of physics might allow several possible outcomes. Our universe would simply represent one realization among many possibilities. This idea becomes especially important when physicists study the early universe. During the first moments after the Big Bang, the conditions of the cosmos were extremely energetic. Fields that are now stable may once have existed in excited or unstable states. As the universe expanded and cooled, these fields gradually settled into their current configurations. But in a vast cosmos, different regions might have followed slightly different paths. Some regions could have settled into one valley of the energy landscape, while others might have fallen into another. Each region would still obey the same underlying physical framework, yet the details of particle properties and forces might differ. This possibility offers a natural way to imagine how different universes might arise. Instead of requiring entirely separate sets of laws, the multiverse could emerge from different regions settling into different stable configurations of the same fundamental fields. Our universe would then represent one particular arrangement within a much larger spectrum of possibilities. The idea is subtle, but powerful. It suggests that the physical constants we measure, such as the masses of particles or the strengths of forces, may not be uniquely determined by the deepest laws of nature. Instead, they might depend on which valley of the cosmic landscape our region happened to settle into during the early history of the universe. This shift in perspective changes how physicists think about the nature of physical law. Rather than asking why the universe follows exactly one set of rules, scientists begin to ask why our region of reality settled into the specific configuration we observe. And once that question is raised, the concept of a multiverse becomes much more natural. If multiple stable configurations are possible, then different regions of reality could embody different versions of physics. Some universes might produce stars and galaxies similar to our own. Others might have particles that behave very differently. Still others might evolve in ways that make complex structures impossible. The deeper theories of particle physics begin to hint that such a landscape of possibilities may exist. Among the fields that play a central role in this story is one that quietly permeates the entire universe, a field responsible for giving particles their mass, a field known as the Higgs field. Understanding how this field behaves may reveal one of the clearest examples of how different regions of the cosmos could follow slightly different physical rules. By now, we have reached a subtle but important shift in our understanding of the universe. Instead of imagining the laws of physics as rigid instructions permanently fixed across all of reality, modern physics increasingly suggest that many of the properties we observe may arise from deeper structures that fill space itself. These structures are the fields we encountered earlier. Among all the fields known in physics, one in particular plays a quiet but central role in shaping the universe we see around us. It is known as the Higgs field. Unlike many physical concepts that sound dramatic or mysterious, the Higgs field operates in a surprisingly gentle way. It is not a force pulling objects together like gravity, and it is not a wave travelling through space like light. Instead, the Higgs field acts more like an invisible background condition of the universe. It exists everywhere, filling all of space, even in regions that appear completely empty. And yet this quiet field determines one of the most fundamental properties of matter: mass. When we think of mass in everyday life, we usually imagine it as a measure of how heavy something is. A rock has more mass than a feather. A planet has more mass than a rock. But in particle physics, mass has a deeper meaning. It describes how strongly a particle resists changes in motion. A particle with greater mass requires more energy to accelerate or slow down. For a long time, physicists struggled to understand why fundamental particles possess the particular masses we observe. Why do electrons have the mass they do? Why are some particles heavier than others? Why are certain particles nearly massless while others are extremely heavy? The answer, according to modern particle physics, lies in the interaction between particles and the Higgs field. To visualize this idea, imagine a large open room filled with a soft invisible medium, something like a very gentle fog. If a small object moves through that room, it might glide easily without much resistance. But if another object interacts more strongly with the fog, its motion would be slowed more noticeably. In this analogy, The fog represents the Higgs field. Particles moving through space interact with this field in different ways. Some particles couple strongly to the field and therefore behave as if they have greater mass. Others interact only weakly and remain relatively light. This interaction does not involve friction in the ordinary sense. Instead, it reflects how particles respond to the background energy, state of the Higgs field. The existence of this field was confirmed in 2012 when physicists working at the Large Hadron Collider observed the Higgs particle, a small ripple in the Higgs field itself. This discovery confirmed that the field permeates the universe exactly as predicted by the theory. But the Higgs field reveals something even more intriguing. Like the landscape of hills and valleys we discussed earlier, the Higgs field can exist in different energy states. The particular state that our universe occupies determines how strongly particles interact with the field, and therefore how much mass they acquire. In the earliest moments of the universe, the Higgs field may not have been in the stable configuration we observe today. During the extremely hot conditions of the young cosmos, many fields behaved differently. Their energy landscapes were altered by the intense temperature and density. As the universe expanded and cooled, the Higgs field eventually settled into a stable resting state. Physicists sometimes describe this transition as a kind of symmetry breaking. At extremely high energies, certain forces and particles behave in more unified ways. As the universe cools, that symmetry breaks, and the familiar properties of particles begin to emerge. The moment when the Higgs field settled into its current state helped determine the masses of many fundamental particles, and those particle masses influence nearly every aspect of cosmic evolution. They shape how atoms form. They determine the structure of molecules. They influence how stars ignite and how nuclear reactions unfold within stellar cores. In short, the behavior of the Higgs field quietly influences the architecture of the entire universe. Now imagine what might happen if the Higgs field had settled into a slightly different configuration. In another valley of the energy landscape, particles might interact with the field in different ways. Electrons might become heavier or lighter. Quarks, the particles that form protons and neutrons, might have different masses. Even small changes in these properties could have dramatic consequences. Atoms might become unstable. Chemistry might behave very differently. Stars might burn too quickly, or perhaps fail to ignite at all. A universe with different particle masses might look radically different from our own. In some cases, it might not contain the complex structures necessary for galaxies, planets, or life. This possibility illustrates a powerful idea. The laws of physics might not uniquely determine every detail of a universe. Instead, those laws may allow several possible configurations. Our universe represents one particular outcome among those possibilities. And if multiple regions of reality exist, perhaps generated through processes like cosmic inflation, each region might settle into its own configuration of fields. Some universes could have particle masses similar to ours, others might be very different. This concept leads physicists toward a deeper picture of the cosmos. Instead of a single universe with a single set of physical properties, reality might contain a vast collection of universes, each defined by the way fundamental fields settled into stable states during their early histories. But the Higgs field may be only one example. Some theories suggest that the deeper structure of physics could allow an enormous variety of possible configurations. To explore that possibility, physicists have developed theories that attempt to unify all particles and forces into a single framework. Among the most ambitious of these attempts is a theory that proposes that the basic ingredients of reality may not be point-like particles at all. Instead, they may be tiny vibrating strands existing within additional hidden dimensions of space. This framework is known as string theory. and within string theory the number of possible universes may be far larger than anyone once imagined. By now, the possibility that different universes could exist no longer feels like a sudden leap. We have already encountered several ways in which multiple universes might arise. Space itself may extend far beyond our observable horizon, producing distant cosmic regions with different arrangements of matter. Cosmic inflation may generate many bubble universes, each expanding with its own cosmic history. And the behaviour of fundamental fields, such as the Higgs field, suggests that the properties of particles might depend on how those fields settle into stable configurations. Yet there is another idea in theoretical physics that pushes this possibility even further. An idea suggesting that the number of possible universes may not merely be large, it may be staggeringly vast. This idea arises from a framework known as string theory. String theory began as an attempt to answer one of the deepest challenges in modern physics. For more than a century, physicists have relied on two extraordinarily successful theories to describe the universe. One is general relativity, Albert Einstein's theory of gravity, which explains how massive objects curve space and shape the motion of planets, stars, and galaxies. The other is quantum mechanics, the theory that governs the behaviour of particles at the smallest scales. Both theories work extremely well within their own domains. General relativity describes the motion of galaxies and the expansion of the universe. Quantum mechanics describes atoms, particles, and the microscopic world. But when physicists attempt to combine these two theories into a single unified framework, they encounter profound difficulties. The mathematics becomes unstable, and predictions lose their meaning at extremely small scales. String theory was developed as one possible way to resolve this conflict. Instead of treating fundamental particles as tiny point-like objects, string theory proposes that the most basic ingredients of reality may be extremely small vibrating strands. These strands are unimaginably tiny, far smaller than anything we can currently observe directly. Each string can vibrate in different ways, much like a musical string producing different notes. And according to the theory, the pattern of vibration determines what type of particle the string represents. One vibration might correspond to an electron, another vibration might correspond to a particle of light. In this picture, the diversity of particles arises from different vibrational patterns of the same underlying object. While this idea is fascinating on its own, string theory introduces another surprising feature. The theory only works consistently if space contains more dimensions than the three we experience in everyday life. We are familiar with three dimensions of space: length, width, and height. These dimensions describe the directions in which objects can move. But string theory suggests that additional spatial dimensions may exist beyond these familiar ones. These extra dimensions would be extremely small, curled up at scales far too tiny for us to perceive directly. To imagine this, think about a long garden hose lying on the ground. From a distance, the hose appears to be a simple one-dimensional line stretching across the yard. But if you move closer, you can see that the hose has a circular dimension wrapped around it. An ant walking along the hose could move forward and backward along its length, but it could also crawl around the circular surface. In a similar way, the extra dimensions proposed in string theory may be tightly curled shapes, embedded within every point of space. These hidden dimensions are often described using intricate geometric forms known as Calabi-Yau shapes. While the mathematics describing these shapes can become extremely complex, the essential idea is simple. The exact shape of these tiny curled dimensions can influence how strings vibrate. And since string vibrations correspond to particles, the geometry of these hidden dimensions can determine the properties of the particles and forces that appear in a universe. Different shapes could produce different physical rules, One configuration might produce particles with masses similar to those in our universe. Another configuration might generate very different particle properties. In some cases, the resulting universe might not allow stable atoms to form. In others, gravity might behave differently. This means that string theory does not predict just one possible universe. Instead, it allows an enormous variety of possible configurations. Physicists often refer to this collection of possibilities as the string landscape. The landscape is like an immense terrain filled with valleys, each valley representing a different stable configuration of the fundamental fields and dimensions. Every valley corresponds to a possible universe with its own version of physical laws. The number of such possibilities may be astonishingly large. Some estimates suggest that the number of possible configurations could be so vast that writing the number in ordinary notation would require an almost unimaginable string of digits. Rather than trying to visualize the number directly, it is easier to imagine a vast cosmic landscape stretching beyond the horizon. In this landscape, each valley represents a different universe waiting to unfold. Some valleys might produce universes similar to our own. Others might generate universes where stars never form. Some might produce universes where matter behaves so differently that complex structures cannot exist at all. In this way, string theory suggests that the laws of physics we observe may not be uniquely determined. Instead, they may depend on which valley of the landscape our universe occupies. If the multiverse exists, our universe could simply be one region, where the fields and dimensions settled into a configuration compatible with the formation of galaxies, stars, and life. But this possibility leads to a deeper puzzle. If the landscape of possible universes is so vast, why do we find ourselves in one that appears so finely balanced for the existence of complex structures? Why do the constants of nature seem to fall within the narrow range that allows stars to shine, atoms to form, and life to emerge? This question leads us toward one of the most intriguing ideas in modern cosmology, an idea known as the fine-tuning problem. When physicists look closely at the universe, they notice something rather curious. Many of the numbers that describe the laws of nature appear to sit within remarkably narrow ranges. If those numbers were even slightly different, the universe we know might not exist in the same way. Stars might fail to shine, atoms might fail to hold together, or the universe might expand too rapidly for galaxies to form at all. This observation is often described as the problem of fine-tuning. The phrase does not imply intention or design in any philosophical sense. Instead, it simply refers to the surprising sensitivity of the universe to the values of certain physical constants. To understand why this sensitivity matters, it helps to think of the universe as a kind of cosmic recipe. Just as a delicate dessert requires precise amounts of ingredients, the large-scale structure of the universe depends on certain numerical values appearing within specific ranges. Change those ingredients too much, and the result may be entirely different. One example involves the strength of gravity. Gravity is the force that pulls matter together, allowing gas clouds to collapse into stars and galaxies. If gravity were significantly stronger, matter might collapse too quickly, forming extremely dense stars that burn out rapidly or collapse into black holes almost immediately. If gravity were much weaker, gas clouds might never condense enough to ignite nuclear fusion, leaving the universe filled with diffuse clouds of cold gas. Either extreme would make the formation of long-lived stars far less likely. Another example involves the electromagnetic force, which governs how atoms and molecules interact. This force holds electrons around atomic nuclei, allowing chemistry to exist. If the strength of this interaction were altered significantly, atoms might become unstable. Electrons might escape their orbits, or atoms might bind together too tightly for complex chemistry to occur. Without stable atoms and chemical bonds, the molecules necessary for life could never form. The balance between the electromagnetic force and the nuclear forces inside atoms is also crucial. Inside every atomic nucleus, protons are packed together in extremely small spaces. Because protons carry positive electric charge, they naturally repel one another, yet the strong nuclear force acts as a kind of glue, holding these particles together. If the nuclear force were even slightly weaker, atomic nuclei might not remain stable. If it were significantly stronger, nuclear reactions inside stars might behave very differently. Even the number of spatial dimensions plays a role in this delicate balance. In our universe, space has 3 dimensions that we can move through freely. If there were more large dimensions of space, the behavior of gravity and electromagnetism would change dramatically. Stable planetary orbits might not exist. Atoms themselves might become unstable. The fact that we live in a universe with exactly 3 large spatial dimensions appears to be deeply connected to the possibility of complex structures. Another remarkable example involves the energy associated with empty space itself. Physicists call this quantity dark energy. Dark energy influences how quickly the universe expands. If this energy were much larger than the value we observe, space would expand so rapidly that matter would never have time to gather into galaxies. If it were significantly smaller or negative, gravity might eventually cause the universe to collapse back inward, long before stars and planets had time to form. The value we observe appears small but non-zero, allowing cosmic structures to develop over billions of years. Each of these examples illustrates a similar theme. The universe seems to occupy a narrow range of conditions that allow complexity to emerge. Stars shine steadily, atoms remain stable, chemistry unfolds in intricate ways, galaxies form and evolve over cosmic time. Many scientists have reflected on this pattern with quiet curiosity. Why should the laws of nature fall within these particular ranges? One possibility is that the values we observe are simply fundamental properties of reality. Perhaps there is only one possible universe, and these numbers could never have been different. But as modern theoretical physics has progressed, another possibility has begun to take shape. If the multiverse exists, then many different universes might exist with different combinations of physical constants. In that case, most universes might not allow complex structures to form. Only a small fraction would possess the delicate balance necessary for long-lived stars, stable atoms, and complex chemistry. If observers arise only in those rare universes where such conditions exist, then it is not surprising that we find ourselves in one of them. This line of reasoning leads toward a concept that has generated both fascination and debate among scientists. It is known as the anthropic principle. The anthropic principle does not claim that the universe was designed for observers. Instead, it simply acknowledges a selection effect. Observers can only appear in regions of reality where the conditions allow them to exist. In a vast multiverse containing many different physical possibilities, we would naturally find ourselves in a universe where the cosmic ingredients happen to support complexity. At first glance, this idea can feel unsettling. It shifts the question from why does the universe have these properties to among many possible universes, why do we happen to observe this particular one? Yet for many physicists, the concept provides a possible way to understand the fine-tuning puzzle, and surprisingly, in at least one case, this line of thinking led to a prediction about the universe before the relevant measurement had been made. That story, involving the mysterious energy of empty space, would become one of the most intriguing intersections between the multiverse idea and real astronomical observations. The puzzle of fine-tuning leads naturally to a deeper and somewhat unusual question. If the laws of physics could take many possible forms, and if many universes exist where those laws differ slightly, then why do we observe a universe that appears so carefully balanced for complexity? One possible answer lies not in the universe itself, but in the simple fact that we are here to observe it. This idea is known as the anthropic principle. Despite its somewhat philosophical name, the anthropic principle is actually a fairly straightforward observation. It simply states that any universe capable of being observed must contain conditions that allow observers to exist. That may sound almost trivial at first. But when applied to a multiverse containing many different universes with different physical properties, the idea becomes surprisingly powerful. Imagine a vast cosmic collection of universes. In some of these universes, gravity might be too strong, causing matter to collapse rapidly into dense objects where stable stars cannot survive. In others, gravity might be too weak, preventing gas from gathering into stars at all. Some universes might expand so quickly that galaxies never have time to form. Others might collapse back inward too quickly for complex structures to develop. In most of these universes, observers might never arise. There would be no astronomers, no scientists, and no curious minds asking questions about the cosmos. But in a small fraction of universes, the conditions might fall within a narrow window that allows stars to burn steadily, atoms to form stable molecules, and chemistry to unfold in rich and complex ways. In those rare universes, observers might eventually appear, and naturally any observers who do appear would find themselves living in one of the universes where the conditions allowed their existence. In other words, the very act of observing the universe already filters the possible environments in which observation can occur. To illustrate this idea with a simpler example, imagine walking into a vast library containing millions of books. Most of the books might be written in languages you cannot understand. Only a few might be written in a language you can read. If you begin exploring the library, you would naturally spend most of your time reading the books written in your language. From your perspective, the library might seem unusually rich in readable books, but in reality, your ability to read those books has simply filtered which ones you notice. The anthropic principle suggests something similar about the universe. Among a vast range of possible universes, observers will naturally appear only in the small subset where physical conditions permit complexity. For many years, this idea remained largely philosophical. Some scientists viewed it with skepticism, arguing that it did not provide concrete predictions. But in the late 20th century, an intriguing development changed that perception. The development involved one of the most mysterious quantities in cosmology: the energy associated with empty space. Earlier we mentioned that empty space is not truly empty. Even in regions devoid of matter, quantum physics predicts that fields still exist, and these fields possess energy. This energy contributes to the expansion of the universe. Physicists often describe it using a quantity called the cosmological constant. This constant represents the energy density of empty space itself. The puzzling part is that theoretical calculations suggest that this energy could be enormously large. Yet astronomical observations show that the actual value of this energy is extremely small. Not exactly zero, but small enough to allow galaxies to form over billions of years. For decades, physicists struggled to understand why the cosmological constant should take such a tiny value. Then, in 1987, physicist Steven Weinberg proposed an intriguing line of reasoning. If many universes exist with different values of the cosmological constant, then most universes might have values that are too large. In those universes, space would expand so rapidly that matter would never clump together to form galaxies. Without galaxies, stars would not form. Without stars, planets and chemistry would not arise. In other words, observers would never appear, but in universes where the cosmological constant happens to be small enough, galaxies could form. stars could ignite, planets could develop, observers might eventually emerge. Weinberg reasoned that if the multiverse idea were correct, then the cosmological constant we observe should lie near the largest value that still allows galaxies to form, not extremely tiny, but just small enough to permit cosmic structure. At the time, the true value of this constant had not yet been measured. Then, in the late 1990s, astronomers studying distant exploding stars made a surprising discovery. They found that the expansion of the universe is accelerating. The most natural explanation for this acceleration is a small but positive cosmological constant. And remarkably, the measured value turned out to fall within the general range predicted by Weinberg's anthropic reasoning. This result did not prove that the multiverse exists, but it demonstrated that anthropic reasoning could lead to meaningful expectations about observable quantities. Instead of being purely philosophical, the idea had made contact with real measurements. Still, many physicists remain cautious. Some argue that anthropic reasoning risks becoming too flexible. If every unexplained feature of the universe is attributed to the existence of many universes, the idea might become difficult to test. Others argue that anthropic reasoning may simply reflect the limits of our current understanding. Perhaps a deeper theory will one day explain why the constants of nature take the values they do, without requiring a multiverse at all. The debate continues. But regardless of where the truth ultimately lies, the anthropic principle offers an intriguing perspective. It reminds us that the universe we observe may be only one chapter in a much larger cosmic story. A story in which countless universes may exist, each with its own physical character, quietly unfolding across a vast and largely unseen reality. And this raises a deeper question. If the multiverse might explain fine-tuning, does it also challenge one of the most important guiding principles in science? The principle known as Occam's razor. At this point in our journey, the idea of a multiverse may feel both fascinating and slightly unsettling. On one hand, modern theories in cosmology and particle physics seem to naturally allow the possibility that many universes could exist. Inflationary cosmology may produce vast numbers of bubble universes. Quantum theory may permit many parallel branches of reality. And theories like string theory suggest an enormous landscape of possible physical configurations. Yet there is a question that often arises whenever this idea is discussed. Isn't the multiverse simply too extravagant? Doesn't proposing countless universes violate one of the most famous principles in science? A principle known as Occam's razor. Occam's razor is often summarized in a simple phrase. The simplest explanation is usually the best one. The idea is named after the 14th century philosopher William of Ockham, who argued that when multiple explanations can account for the same observation, we should prefer the explanation that makes the fewest unnecessary assumptions. At first glance, the multiverse seems to conflict directly with this principle. After all, proposing a single universe seems simpler than proposing an enormous collection of universes. Why introduce countless unseen worlds if one universe appears sufficient to explain our observations? This criticism has led some scientists to view the multiverse idea with caution. They worry that it may represent an explanation that multiplies entities beyond necessity. However, the situation becomes more subtle when we examine what Occam's razor actually requires. Occam's razor does not say that reality itself must be simple. Instead, it says that our explanations should avoid adding unnecessary assumptions. In other words, the principle is about the structure of theories, not about how many objects exist in the universe. Sometimes a theory that appears simple on the surface may actually require many hidden assumptions, and sometimes a theory that predicts a large number of objects may arise naturally from a small and elegant set of principles. Consider an example from the history of astronomy. Before the 17th century, Many people believe that Earth sat at the centre of the universe, with the sun, moon, and planets moving around it. This model seemed simple and intuitive, but as astronomers collected more precise observations of planetary motion, they discovered that the geocentric model required increasingly complicated adjustments. Astronomers introduced circles within circles known as epicycles to account for the strange looping motions of planets in the sky. Over time, the model became more and more complex. Eventually, Nicholas Copernicus proposed a different explanation. In his model, the sun sat at the centre of the planetary system, and Earth moved around it. At first glance, this model seemed to introduce an additional moving object, Earth itself. But the overall structure of the theory was actually simpler. Planetary motions became easier to explain. Later refinements by Johannes Kepler and Isaac Newton revealed deeper mathematical patterns underlying planetary orbits. In this case, the simpler theory did not reduce the number of objects in the universe. Instead, it reduced the number of assumptions needed to describe how those objects behaved. A similar situation may apply to the multiverse. If a single elegant theory of physics naturally predicts that many universes will exist, then the presence of those universes may not represent an additional assumption. Instead, they may simply be consequences of the underlying theory. For example, eternal inflation arises naturally from certain models of cosmic inflation. Once the process begins, the mathematics suggests that inflation may continue in different regions of space indefinitely, producing new bubble universes along the way. In this case, the existence of many universes is not an extra hypothesis added afterward. It is a prediction of the theory itself. Similarly, if string theory truly describes the fundamental structure of reality, the enormous landscape of possible vacuum states may arise automatically from the mathematics of the theory. Physicists would not be inventing these universes arbitrarily. They would simply be acknowledging the range of possibilities allowed by the theory. From this perspective, rejecting the multiverse might actually require adding new assumptions that restrict the theory in ways not supported by the mathematics. Of course, this argument does not settle the question completely. Even if a theory predicts many universes, scientists still want to know whether the theory itself is correct. And this leads to another important issue. Scientific ideas must ultimately connect to observation. A theory that predicts invisible universes must still produce consequences that we can test in some way. Otherwise, it risks drifting away from the realm of empirical science. This concern leads to one of the most important debates surrounding the multiverse. Can the multiverse ever be tested, or is it fundamentally beyond the reach of observation? Some critics argue that because other universes may lie forever beyond our cosmic horizon, they could never be observed directly. If that is true, they suggest the multiverse might belong more to philosophy than to science. Others argue that even if other universes cannot be seen directly, their existence might still leave subtle traces in the structure of our own universe. Patterns in cosmic background radiation, predictions about fundamental constants, statistical expectations about cosmic properties. These possibilities hint that the boundary between science and speculation may not be as rigid as it first appears. The multiverse may sit at the edge of what science can currently explore, and in that quiet boundary between the known and the unknown, physicists continue to search for clues that might one day reveal whether our universe is truly alone, or whether it is just one small island in a far larger cosmic ocean. One of the most common questions raised about the multiverse is both simple and profound. If other universes exist, can we ever actually test the idea? Science has traditionally relied on observation and experiment. A scientific theory is expected to make predictions that can be compared with measurements of the real world. If those predictions fail, the theory must be revised or abandoned. Because of this principle, critics sometimes argue that the multiverse may fall outside the boundaries of science. If other universes lie beyond our observable horizon, they might never be directly detected. In that case, how could we confirm that they exist? This concern touches on a concept often called falsifiability. The idea introduced by philosopher Karl Popper suggests that a scientific theory should make predictions that could, at least in principle, be proven wrong by observation. If a theory cannot possibly be contradicted by any observation, then some philosophers argue that it may not qualify as scientific. At first glance, the multiverse appears to face this challenge. If each universe is separated by vast regions of space expanding faster than light can travel, then no signal from these regions could ever reach us. Even if countless universes exist beyond our cosmic horizon, we might never see them directly, but the situation is more subtle than it first appears. Science often deals with entities that cannot be observed directly. Instead, scientists infer their existence from indirect evidence. For example, consider black holes. For many decades after Einstein's theory of general relativity predicted them black, holes could not be observed directly. Astronomers could only infer their presence from the motion of nearby stars or from the radiation emitted by matter falling into them. Yet these indirect observations gradually built a convincing case. Eventually, technological advances allowed astronomers to capture images of the shadow of a black hole, confirming the theory more directly. Another example comes from the early history of atomic theory. Long before microscopes capable of imaging individual atoms existed, scientists inferred the existence of atoms from chemical reactions and patterns in the behavior of gases. Atoms were not seen directly, but the theory made predictions that could be tested through experiment. Over time, these predictions consistently matched observation. Eventually, technology caught up with theory, and atoms themselves became visible through powerful microscopes. In both of these cases, scientific ideas began as theoretical explanations supported by indirect evidence. Only later did direct observations become possible. The multiverse may follow a similar path. Even if we cannot observe other universes directly, theories that predict a multiverse may still make testable predictions about the universe we inhabit. For example, models of cosmic inflation predict certain patterns in the faint radiation left over from the early universe. This radiation is known as the cosmic microwave background. It fills the entire sky and carries subtle patterns imprinted during the universe's earliest moments. Precise measurements of this radiation have allowed scientists to test many predictions of inflationary cosmology. If inflation is confirmed by observation, and if certain versions of inflation naturally produce many universes, then the multiverse becomes a possible consequence of a theory that is itself testable. Similarly, if a fundamental theory, such as string theory, eventually produces predictions about particle properties that match experimental results, then the broader framework of that theory may gain credibility. Even if we cannot observe every consequence of the theory directly, its success in explaining observable phenomena would strengthen the case for its deeper structure. Another possibility involves subtle signatures that might appear if our universe once interacted with another. Some models suggest that if two expanding bubble universes collided early in cosmic history, the event might leave faint circular patterns in the cosmic microwave background. Astronomers have searched for such patterns in detailed maps of the early universe. So far, no clear evidence of such collisions has been found. But the search itself demonstrates an important point. Scientists are actively exploring ways to test the idea. Even when direct observation is impossible, indirect clues may still be within reach. In cosmology, this situation is not unusual. The observable universe itself has limits. Light travels at a finite speed, and the universe has existed for about 13.8 billion years. Because of this, there are regions of space so distant that their light has not yet reached us. Those regions are real parts of the universe, even though we cannot observe them directly. Cosmologists accept their existence because they arise naturally from well-tested theories of cosmic expansion. The multiverse may represent a similar extension of scientific reasoning. If a theory that successfully explains observable phenomena also predicts the existence of other universes, then scientists must consider that possibility seriously. Of course, caution remains essential. Scientists must be careful not to accept explanations too quickly without sufficient evidence. The boundary between science and speculation must be approached with humility and critical thinking. But the history of science reminds us that today's speculative idea may become tomorrow's confirmed discovery. Concepts once considered abstract, from atoms to black holes to gravitational waves, eventually became observable realities. Whether the multiverse will follow the same path remains unknown. For now, it sits at the frontier of our understanding, a place where theory, observation, and imagination meet. And in that quiet frontier, physicists continue searching for new clues that might one day reveal whether our universe truly stands alone, or whether it is part of a far greater cosmic tapestry. If the multiverse exists, it may lie far beyond the reach of direct observation. Other universes might be separated from ours by immense stretches of expanding space, or by boundaries that light itself can never cross. Yet scientists have not stopped looking for clues. Even if we cannot travel to other universes or receive signals from them directly, it is still possible that their existence might leave subtle fingerprints in the structure of our own universe. To understand how such clues might appear, we need to look at one of the most remarkable sources of information about the early cosmos, a faint glow that fills the entire sky. This glow is known as the cosmic microwave background. Long ago, about 380,000 years after the universe began expanding, the cosmos had cooled enough for atoms to form for the first time. Before that moment, the universe was filled with a hot plasma of charged particles and light. Photons were constantly scattering from electrons, preventing light from travelling freely through space. But as the universe expanded and cooled, electrons joined with atomic nuclei to form neutral atoms. When that happened, light was finally able to travel through space without being constantly scattered. The photons released at that moment have been travelling across the universe ever since. Over billions of years, the expansion of space stretched their wavelengths, transforming that ancient light into microwave radiation. Today, this radiation still fills the entire sky. It forms a kind of cosmic photograph of the universe when it was still very young. Modern satellites have mapped this faint radiation with extraordinary precision. These maps reveal tiny temperature variations across the sky, differences so small that they represent changes of only a few millionths of a degree. Yet these small variations carry enormous information. They reveal how matter was distributed in the early universe, and how the first seeds of galaxies began to form. Because the cosmic microwave background preserves such a detailed picture of the young universe, scientists have wondered whether it might also contain hints of interactions with other universes. One intriguing possibility arises from certain models of cosmic inflation. In these models, many bubble universes may form within an expanding cosmic background. If two of these bubble universes happen to form close enough together, they might collide as they expanded. Such a collision would not resemble the dramatic explosions we might imagine in science fiction. Instead, it would occur at the boundaries between two expanding regions of space-time. The interaction might disturb the distribution of energy in the early universe, and that disturbance could leave subtle marks in the cosmic microwave background. Some researchers have proposed that these marks might appear as faint circular patterns in the temperature map of the sky. These circles would represent regions where the structure of the early universe was slightly altered by a collision between two bubble universes. Over the past 2 decades, astronomers have searched for such patterns in detailed maps produced by space missions such as the Wilkinson Microwave Anisotropy Probe and the Planck satellite. So far, the evidence remains inconclusive. Some studies have identified patterns that might resemble the predicted signals, while others suggest that those patterns can be explained by ordinary statistical variations in the cosmic background. The search continues. Even if these particular signals are not found, the process of searching teaches scientists how to refine their models and understand the universe more deeply. Another possible clue involves the large-scale structure of the cosmos. When astronomers map the distribution of galaxies across the universe, they find that matter forms an intricate cosmic web. Galaxies cluster along enormous filaments stretching across hundreds of millions of light years, while vast empty regions known as cosmic voids lie between them. This structure reflects the gravitational growth of tiny fluctuations that were present in the early universe. Some researchers have wondered whether unusual patterns in this cosmic web might hint at influences beyond our observable universe. For example, if the laws of physics varied slightly in distant regions during the earliest moments of cosmic inflation, those variations might influence the distribution of matter on the larger scales. Such effects would be extremely subtle. Detecting them would require enormous surveys of galaxies and extremely precise statistical analysis. Yet new telescopes and sky surveys are steadily improving our ability to measure the universe on these vast scales. Another avenue of investigation involves gravitational waves. These are ripples in space-time itself, produced when massive objects accelerate or collide. The early universe may have produced a faint background of gravitational waves during cosmic inflation. If certain multiverse models are correct, collisions between bubble universes might have generated additional gravitational wave signals. Future detectors designed to measure extremely faint gravitational waves could potentially search for such patterns. All of these possibilities share a common theme. Scientists are searching for indirect signals. They're looking for patterns in the structure of our universe that might hint at events or processes beyond our cosmic horizon. Whether these searches will ever reveal clear evidence remains uncertain. The universe is vast and the signals we seek may be extremely faint. Yet the effort itself reflects one of the most beautiful aspects of science: curiosity. The willingness to explore even the most distant possibilities, guided by careful reasoning and observation. And as we continue looking outward into the deep sky, another possibility emerges from an entirely different branch of physics, a possibility suggesting that multiple versions of reality may not exist only across vast distances of space. They may exist within the very structure of quantum events themselves. So far in our journey, the idea of multiple universes has mostly appeared on the largest scales imaginable. We've explored the possibility that distant regions of space may extend far beyond our cosmic horizon. We've considered inflationary cosmology, where expanding bubbles of space-time may give birth to separate universes, and we've seen how fundamental fields and hidden dimensions might allow many different versions of physics to emerge. But there is another route to the multiverse, and surprisingly it begins not with galaxies or cosmic inflation, but with the strange behaviour of particles on the smallest imaginable scales. This route emerges from quantum mechanics. Quantum mechanics is the theory that describes how particles behave at extremely small distances. At these scales, nature does not always behave in the familiar way we experience in everyday life. Instead, particles can exist in states that appear almost paradoxical. One of the most famous examples is known as quantum superposition. In classical physics, an object must have a definite state. A coin is either heads or tails. A light switch is either on or off. but quantum systems can exist in combinations of possibilities. Before measurement, a particle may exist in a mixture of several potential states simultaneously. Physicists often describe this situation using a mathematical object known as the wave function. Rather than assigning a single position or motion to a particle, the wave function describes a range of possible outcomes and the relative likelihood of each. You can imagine it as a kind of cloud of possibilities. Within that cloud, the particle does not occupy one definite location until an interaction occurs that reveals one outcome. This leads to a famous puzzle known as the measurement problem. If quantum systems exist in combinations of possible states, why do we observe definite outcomes? Why do we never see objects that appear half in one state and half in another? For decades, physicists have debated how to interpret this transition from possibility to reality. One traditional explanation suggests that when a measurement occurs, the wave description of the system suddenly collapses into a single outcome. In other words, many possible outcomes exist before measurement, but only one becomes real. However, in the middle of the 20th century, a young physicist named Hugh Everett proposed a different interpretation. Instead of assuming that the wave description collapses, Everett suggested that all possible outcomes might actually occur. According to this interpretation, the universe does not select one outcome and discard the others. Instead, reality branches. Every possible outcome continues to exist, but in separate branches of the universe. This idea became known as the many worlds interpretation of quantum mechanics. In this view, the wave description of reality never collapses. Instead, the universe constantly divides into multiple branches, each representing a different outcome of quantum events. To imagine how this works, consider a simple quantum experiment. Suppose a particle can travel through two different paths. Before observation, the particle behaves as if it explores both possibilities simultaneously. When a measurement occurs, we observe the particle travelling along one specific path. In the many worlds interpretation, both outcomes still exist. In one branch of reality, the particle travels along the first path. In another branch, it travels along the second path. Each branch evolves independently from that moment forward. From the perspective of observers within one branch, it appears as though a single outcome occurred. But the broader structure of reality contains all possible results. This interpretation suggests that quantum events continually produce branching histories of the universe. Every interaction that involves quantum uncertainty could generate new branches of reality. Most of these differences would be extremely small. In one branch, a photon might scatter slightly differently. In another branch, a molecule might take a slightly different path. Yet over long periods of time, these small differences could accumulate. Entire histories of the universe could diverge. In some branches, events unfold almost exactly as they do in our familiar world. In others, the differences might eventually become dramatic. Galaxies may form in slightly different ways. Stars may evolve along different paths. Even the history of life on a planet might diverge in subtle ways. It is important to understand that these branches would not be separate universes located somewhere else in space. Instead, they would exist as parallel histories embedded within the mathematical structure of quantum reality. Once branches separate, they no longer interact. Each branch evolves as if the others were invisible. This idea remains one of the most debated interpretations of quantum mechanics. Some physicists find it compelling because it preserves the mathematical structure of quantum theory without introducing additional mechanisms such as wave collapse. Others feel that the idea introduces an enormous number of unseen worlds without providing clear observational evidence. Yet the many worlds interpretation illustrates something remarkable. Even without cosmological inflation or string landscapes, The basic equations of quantum mechanics may already contain the seeds of a multiverse, and if this interpretation is correct, the multiverse would not merely exist on distant cosmic scales, it would exist in the very fabric of every quantum interaction, every moment of uncertainty, every branching possibility. Reality itself might resemble a vast tree of histories quietly growing through time, each branch representing a different unfolding of events. Most of these branches would remain forever inaccessible to us, but their existence would reflect the deep structure of quantum theory. And this raises a fascinating question. If reality truly branches into countless parallel histories, what does that mean for our understanding of the universe we experience? If the many worlds interpretation of quantum mechanics is correct, the universe may be far more layered than it first appears, not in the sense of stacked worlds hidden somewhere in distant space, but in the sense that reality itself may continually unfold into many possible histories. Each moment of quantum uncertainty may allow several outcomes, and rather than choosing only one path, the deeper structure of reality may allow every possibility to continue. From our everyday perspective, however, we experience only one of these histories. You wake up in the morning, walk through your day, and remember a single sequence of events. The past feels fixed. The future feels open but singular. Yet beneath this familiar flow of experience, quantum theory suggests something subtler may be happening. At microscopic scales, particles constantly interact, scatter, and exchange energy. Each interaction carries small uncertainties. A photon might bounce slightly differently from an atom. An electron might shift along one possible path rather than another. In classical physics, these differences would simply represent small variations within a single unfolding history. But in the many worlds picture, each possible outcome may correspond to a separate branch of reality. To visualize this, imagine standing at the trunk of a large tree. From the trunk, branches spread outward. Each branch then divides again and again into smaller branches. Over time, the tree expands into a vast network of pathways. In this analogy, the trunk represents the shared past of the universe. The branches represent the many ways events could unfold. Every time a quantum interaction allows multiple outcomes, the tree of reality may quietly grow another set of branches. Most of these differences are unimaginably small. In one branch, a photon might scatter slightly differently. In another branch, a molecule in the atmosphere might move along a slightly different trajectory. At first, these differences may seem insignificant, but over long periods of time, tiny differences can accumulate. Weather systems may evolve differently, planetary environments may shift along slightly altered paths, biological evolution might follow new trajectories, entire civilizations might develop in different ways. From our perspective inside one branch, however, none of this branching is visible. Why? Because of a process known as decoherence. Decoherence describes how quantum systems interact with their surroundings. When a quantum system becomes entangled with its environment, the delicate superposition of possibilities effectively separates into distinct branches that no longer interfere with one another. In simpler terms, once different outcomes interact with the surrounding world, the branches become independent. They stop affecting each other. It becomes impossible to combine them again into a single shared state. Imagine two ripples spreading across the surface of a pond. If the ripples overlap, they can interfere with each other, forming complex patterns. But if the ripples travel far apart across the water, they eventually become completely separate waves. Something similar happens in quantum branching. Once branches diverge and interact with the environment, they evolve independently. From the perspective of observers within one branch, it appears as though only one outcome ever occurred. The other possibilities become inaccessible. They exist if the many worlds interpretation is correct, but they lie beyond the reach of any experiment we could perform within our branch. This independence explains why the world around us feels stable and consistent. We do not see objects flickering between possibilities. We see definite outcomes, because we ourselves are part of a particular branch of the quantum history of the universe. Our memories, our observations, and the physical environment around us all belong to the same branch. From within that branch, the universe appears singular, but the deeper mathematical description of quantum theory may contain many such branches evolving simultaneously. If this picture is correct, the multiverse may not only exist across vast cosmic distances, it may also exist across the branching structure of quantum events. In this sense, the multiverse becomes not just a cosmological idea, but a fundamental feature of reality itself. A quiet branching of possibilities unfolding moment by moment. Of course, the many worlds interpretation remains one among several ways physicists attempt to understand quantum mechanics. Other interpretations propose different mechanisms for how quantum possibilities become definite outcomes. Some suggest that wave descriptions truly collapse during measurement. Others explore new physical processes that might explain the transition between possibilities and reality. The debate continues. Yet regardless of which interpretation ultimately proves correct, quantum mechanics has already taught us something remarkable. The universe is not as simple as it first appears. At its deepest levels, reality may involve layers of possibility and structure far richer than our everyday experience suggests. And whether those possibilities unfold as parallel quantum histories or as distant bubble universes across cosmic space, the idea of a multiverse invites us to reconsider our place in the cosmos. Perhaps our universe is not the whole story. Perhaps it is one thread woven into a far larger tapestry of reality. And if that is true, the question becomes even more profound. What does the existence of many universes mean for science itself? As our journey through the idea of the multiverse slowly draws toward its final reflections, it is worth pausing to consider a deeper question. What does the multiverse actually mean for science? Is it a genuine scientific prediction emerging naturally from our best theories of physics? Or is it an idea that stretches beyond what science can truly confirm? To answer this question, it helps to remember how science has always progressed. Scientific discovery rarely moves forward in perfectly straight lines. Instead, it often advances through a mixture of careful observation, mathematical reasoning, and imaginative exploration. Sometimes theories appear before technology exists to test them. At other times, unexpected observations force scientists to invent entirely new theories to explain what they see. The relationship between theory and observation is a quiet dance that unfolds across decades or even centuries. The idea of atoms offers a helpful example. More than 2,000 years ago, ancient philosophers suggested that matter might be composed of tiny indivisible units. At the time, this was little more than speculation. No experiment could confirm the existence of such particles. For centuries, the idea remained a philosophical concept rather than a scientific one. Then, in the 19th century, chemists studying the behavior of gases and chemical reactions began to find patterns that strongly suggested matter was indeed composed of discrete particles. Atoms gradually became a scientific theory supported by evidence, and eventually, with the development of powerful microscopes and particle detectors, scientists were able to observe individual atoms directly. An idea that once seemed purely theoretical became an observable feature of reality. Something similar happened with gravitational waves. In 1916, Albert Einstein's theory of general relativity predicted that accelerating masses could create ripples in the fabric of space-time. These ripples would travel across the universe at the speed of the light. For nearly a century, however, gravitational waves remained undetected. Their effects were simply too small to measure with existing instruments. But physicists continued refining their understanding of the theory and improving experimental technology. Finally, in 2015, detectors in the United States recorded the first direct observation of gravitational waves produced by the collision of two black holes. Once again, a theoretical prediction eventually became observable. These examples remind us that scientific ideas sometimes live for long periods in a state of partial uncertainty. They are supported by strong theoretical reasoning but await future observations to confirm or refute them. The multiverse may currently occupy such a position. Some of the most successful theories in modern physics appear to allow or even predict the existence of many universes. Inflationary cosmology suggests that space may continue expanding in different regions, creating separate cosmic domains. String theory proposes an enormous landscape of possible physical configurations. Quantum mechanics, in some interpretations, implies branching histories of reality. Each of these frameworks arises from attempts to explain observations about our universe. The multiverse does not appear out of nowhere as an arbitrary idea. Instead, it emerges as a possible consequence of deeper theories. Yet, there is an important difference between allowing the multiverse and proving that it exists. Science ultimately depends on evidence. Theories must eventually confront observation. Until direct or indirect evidence clearly points toward the existence of other universes, the multiverse will remain a hypothesis. A compelling one, perhaps, but still incomplete. This situation has led to thoughtful debate within the scientific community. Some researchers argue that the multiverse represents the natural next step in cosmology. They believe that as our understanding of the universe deepens, the existence of many universes may become as widely accepted as the existence of galaxies beyond our own. Others remain cautious. They worry that if the multiverse cannot be tested clearly, it might weaken the boundary between science and speculation. These concerns are not signs of disagreement for its own sake. They are part of the healthy process through which science refines its ideas. Questions, criticism, and careful examination are essential tools in the search for truth. Over time, new observations may tip the balance. Future telescopes may measure the cosmic background radiation with even greater precision. New particle experiments may reveal clues about the structure of fundamental fields. Gravitational wave detectors may uncover signals from the earliest moments of the universe. Each discovery will help scientists refine their understanding of the cosmos, and with each step, the idea of the multiverse will either gain stronger support or gradually fade in favour of new explanations. But regardless of the final outcome, the exploration of the multiverse reveals something deeply human about science. It shows that curiosity does not stop at the edge of what we can currently observe. Instead, curiosity gently pushes outward, asking questions about what might lie beyond the horizon of our knowledge, and sometimes those questions lead to entirely new ways of understanding the universe. Perhaps the multiverse is real. Perhaps our universe is only one small region within a far larger reality. Or perhaps future discoveries will reveal a different explanation for the mysteries we see today. For now, the question remains open, and that openness is part of what makes science such a beautiful journey, a journey that continues to expand our view of the cosmos and our place within it. As our journey through the idea of the multiverse slowly comes to rest, it is worth taking a quiet moment to reflect on the path we've travelled. We began with a simple question: could our universe be only one among many? At first, the idea might have seemed like something drawn from science fiction. Yet as we explored modern physics, we discovered that the concept does not appear only in imaginative storytelling. Instead, it emerges naturally from several serious attempts to understand the deepest structure of reality. We learned that the universe we observe is limited by a horizon. Light travels at a finite speed, and because the cosmos has existed for about 13.8 billion years, there are regions of space whose light has not yet had time to reach us. Beyond that horizon may lie enormous expanses of space we cannot yet observe. In an infinite universe, distant regions could exist where matter is arranged in different patterns, producing environments very different from our own. Then we encountered the idea of cosmic inflation, a rapid expansion in the earliest moments of the universe that may have stretched space faster than light itself can travel. Some versions of this theory suggest that inflation might continue indefinitely in different regions of space. If so, our universe could be one expanding bubble among many others, each bubble forming its own cosmos with its own history. We also explored how the laws of physics might not be completely fixed. Fields such as the Higgs field can settle into different stable states, influencing the masses of particles and the behavior of matter. The deeper framework of string theory suggests that hidden dimensions of space may exist, curled into intricate geometric shapes. Different shapes could produce different physical properties. Together, these possibilities form what physicists sometimes call a landscape of universes, a vast range of possible cosmic environments. Some might resemble our universe, others might differ dramatically. In many of them, stars might never ignite, atoms might not remain stable, complex chemistry might never arise. This observation led us to the puzzle of fine-tuning. The remarkable fact that the physical constants in our universe fall within narrow ranges that allow stars, galaxies, and life to exist. The anthropic principle offers one possible explanation. If many universes exist with different properties, observers would naturally find themselves in those rare universes where the conditions allow them to exist. We also considered the philosophical debates surrounding the multiverse. Does proposing countless universes violate the principle of simplicity known as Occam's razor? Or might those universes arise naturally as predictions of deeper theories? And we explored the question of testability. Scientists are searching for subtle clues in the cosmic microwave background, in gravitational waves, and in the large-scale structure of galaxies. Clues that might hint at events or processes beyond our observable horizon. Finally, we turn to quantum mechanics, a realm where particles behave in ways that challenge our classical intuition. In some interpretations of quantum theory, every possible outcome of a quantum event may continue to exist in separate branches of reality. If this interpretation is correct, the multiverse might not exist only across vast cosmic distances. It might exist within the very structure of quantum events themselves. The universe in that picture becomes a constantly branching tree of possibilities. Yet despite all these ideas, it is important to remember something simple and grounding. Science is a process, not a finished collection of answers. Many of the concepts we explored tonight remain open questions. The multiverse may turn out to be a profound prediction of modern physics, or it may represent a stepping stone toward an even deeper theory that we have not yet discovered. The universe has surprised us many times before. Galaxies beyond our own were once unknown. Black holes were once considered mathematical curiosities. Gravitational waves were once theoretical ripples that seemed impossible to detect. And yet each of these discoveries eventually became part of our scientific understanding of the cosmos. Perhaps the multiverse will follow a similar path, or perhaps it will guide scientists toward entirely new ideas about the nature of reality. For now, the possibility remains open, and there is something quietly beautiful about that openness. It reminds us that the universe is still full of mysteries waiting to be explored. Even after centuries of scientific discovery, we're only beginning to understand the vast structure of the cosmos. Somewhere beyond the limits of what we can see, there may be other universes unfolding their own histories, other galaxies shining under different laws of physics, other cosmic stories quietly unfolding across an unimaginably large reality. Or perhaps our universe truly is unique, a single island of stars surrounded by an endless cosmic ocean. For now, we simply do not know. And perhaps that uncertainty is part of the wonder. The multiverse invites us to look beyond the familiar boundaries of space and time, to imagine a reality larger than anything we have yet observed, a reality where countless possibilities may exist, quietly unfolding across the deep fabric of the cosmos. And as the night grows quiet and your thoughts begin to drift like distant galaxies across the sky, it is comforting to remember that curiosity itself is one of the most powerful forces in science. It gently carries us forward, one question at a time, one discovery after another, until slowly, patiently, the universe reveals a little more of its story. And so, we've reached the end of tonight's exploration. Whether your eyes are still open, or you're already drifting somewhere between waking and dreaming, thank you for spending this quiet journey among the stars. If you'd like to join again for more gentle wanderings through the mysteries of science, you're always welcome to return. For now, the universe continues its silent expansion. Stars continue to shine in distant galaxies, and somewhere, perhaps far beyond what we can see, other universes may be quietly unfolding their own stories in the vast and peaceful darkness of space. Sleep peacefully, wherever and whenever you may be.